Okay, so off we go. Last time we had just skipped over this example to do the following example because it kind of fit in better with the others. I might reorder these in the notes at some point. So how are we going to understand the curve whose polar equation is this right here? Is a temptation to try to play algebraic games to turn everything polar in this equation into something rectangular. And it turns out that's a losing proposition. It just doesn't work out very well. So we're going to take a different approach, and that is basically point plotting, roughly speaking. Now, you can do this one point at a time, but it is extremely tedious, and I think much better ultimately to try to take groups of angles at a time. So I'm going to start by thinking about what's going on in the first quadrant and see what's going on for those values of theta. Of course, that's theta between 0 and pi over 2. All right, so then we're going to plug that in, see what happens to the r's, and then draw the resulting picture. Now, very importantly, a lot of students will look at this and think, okay, well, the angle is going between 0 and pi over 2. You got to keep in mind there are two angles in this story. There's the angle theta, which determines where you are in the picture, but then there's the angle that goes into the sine function. That's 2 theta, not theta, right? So while theta is only going from 0 to pi over 2, the thing that goes into the sine function is going from 0 to pi, which means you're going to get half of a period of a sine wave, which means that if you then look at the corresponding values of r, for these values of theta, and therefore for these values of the argument, r is going to start at 0 and then slowly increase up to 1 and then decrease back down to 0. So that's what we're going to draw on the picture. Now, do keep in mind these are values of r. R is represented as a, air quotes, distance from the origin, right? Of course, this is not necessarily a distance, but anyway, in those green directions, we're going to go these purple distances. And so, for example, as our angle moves along like this, our r's are going to do like this, and all together, so let me clean up the mess, all together that does kind of like this here. Right, so you can see as my angle goes from 0 to pi over 2, how far I'm going in that direction starts at 0, slowly increases up to 1, and then slowly decreases back down to 0. Okay, so the punchline then is that the first part of this curve looks like that. For this curve. Okay, how are we doing? Is everybody on board so far? Okay, let me do the next quadrant because it's a little bit different. Everything else after that I will leave as an exercise for y'all. Whoops. Okay, here we go. Okay, so next. There we go. Okay, so next, looking at these values of theta. Now notice that's from pi over 2 to pi. Second quadrant, right? Now keeping in mind, again, that's not the argument of the sine function, right? What gets plugged in to the sine function is 2 times that. So while theta is only going from pi over 2 to pi, the thing that gets plugged into the sine function goes from pi to 2 pi. And again, it's what you might call the second half of a period of the sine wave. So like so, that means that the values of sine start at 0, go negative, down to -1, and then back up to 0. So now again, this one's a little bit weirder, okay, because all of these r coordinates are negative. And so again, you can't think of it as a distance. It's a coordinate, not a distance. So, for example, as I'm going in that direction, I'm actually going to be back down here, right? So, as I go that way, I'm going to be tracing out a curve down here. So in particular, again, starting at 0 and then getting more negative as your angle moves until it gets to -1. Pretend like these are straight lines. It's harder than it looks. And about like that. Excuse me. So second half, second quadrant, I should say, of this curve continues on from what we had seen before and does like that. Everybody on board? And it continues. Now again, the details I think are a nice exercise for y'all to think through for yourselves, but you can probably even just guess from kind of the pattern that we've got going here. It starts like that, and then it goes like this, and then it'll go over here and do like that, and then it'll come around there and do like that, where it meets back up with where it began, and the whole thing repeats. So this is the resulting curve that we, effectively sort of, one group of angles at a time, we've effectively kind of sort of point plotted. Yeah?
Wait, sorry, how is it? So for the second quadrant, I'm kind of confused on positive, because like when my brain looks at the second, there's like a negative one. So like wouldn't it go in like I don't know.
So for these values of theta, the values of r are negative, which is why those values of theta trace out stuff over here, sort of opposite. Yeah, so it's a little bit of an illusion. I mean, if you look at the eventual picture, there's our eventual picture, and it's tempting to think that this right here is what you get for second quadrant values of theta, but it's not.
Okay.
This is what you get for fourth quadrant values of theta.
Okay.
Yeah, that's right. Yeah, little detail devils. Okay, cool. Moving along, we did this example last time. I won't repeat those details, but I just want to point out that there's kind of another version of this. Now, in the example that we saw last time, we started with polar, and we ended up with the rectangular equation, which we recognize as a circle. I'm going to point out here that you can kind of take it the other direction. Doesn't always work out as conveniently, but in this case it does very nicely, and that is you can go from a rectangular equation to a polar equation. And the good news here is you don't have to actually aim for certain kinds of polar expressions that you have the ability to plug in for. Here we're literally just going to be plugging in existing conversion formulas. Trying to get there we go. Okay. So for example, notice y here. What are we going to do with that y? Do I need to get clever with it and rewrite it in some way before I can write it in polar? Nope. Y is just r sine theta. Just plug it on in there and go ahead. It's all fine. Now, the good news is there are nevertheless some opportunities where, being on the lookout for convenient formulas that, where some of the work has already been done for you is nice. So I like, for example, to note that. So rather than plug in directly from the first equation, just, immediately blinders on, plug in x equals r cosine theta right here, and y equals r sine theta right there, and then multiplying it out, you get a bunch of trig that you then have to deal with. And conveniently, if you square this out first and move terms around, sometimes you can shortcut some of that otherwise ugly trig. So be on the lookout for those kinds of opportunities right there. Last little quick observation I'll make is if you look at these two examples, notice that we have circles centered on the x-axis, tangent to the y-axis, and circles centered on the y-axis, tangent to the x-axis. So these kind of things come up pretty significantly, and notice their equations look pretty similar to each other. Now they're a little bit different. This one up here has a radius of 1/2, centered at 1/2. This has radius 1, centered at 1. They give away that obviously there's a factor of 2 in this equation that's not in that equation, so it all kind of tracks, right? And you can persuade yourself that if you wanted instead this circle to be centered, at K, maybe, radius K, you can probably make a reasonable guess as to how that would be done. And then you can confirm by playing this same algebraic game. So something to think about. It's very nice to know that these kinds of circles are easily represented in polar coordinates. Okay, so moving along, cylindrical coordinates. A lot of people call this polar coordinates in R3. I don't really see the point of that, frankly. You can count syllables. Polar coordinates in R3, I'm pretty sure that's more syllables than cylindrical coordinates. I don't see the advantage then. That it is a different coordinate system for a different space. So why cling to the same name? It just doesn't buy me anything that I see. That said, it is very closely connected to polar coordinates. After all, what we're going to do is for any given point, first thing we're going to do is just project straight down into the xy plane and then write down, I should do it like this, and then write down polar coordinates. And so all of these equations down here that we already knew from polar coordinates still makes perfect sense for cylindrical coordinates as well. So it's important to realize the connection, but let's go ahead and call it something different because it is different. The difference being, of course, that this is three-dimensional. There's also the z-coordinate. So that kind of comes along for the ride. The cylindrical z is exactly the same as the rectangular z. So again, the only thing that's interesting about cylindrical coordinates is that which it has in common with polar coordinates. Okay. All right. So a couple of examples. Keeping in mind that r represents now distance from the z-axis, setting that equal to a constant, hopefully no surprise, gives rise to cylinders, and that's why we call it cylindrical coordinates. I hope that seems reasonable. Okay. All righty. Let's talk about a sphere. Here's the equation of a sphere in rectangular coordinates. How would I write this in cylindrical coordinates if I, for whatever reason, was found that there was a good cause to want to do business in cylindrical instead of rectangular, which, by the way, there will be. Just give it time. How would I do that? And, well, it gets just like with polar. You just kind of make the appropriate substitutions. And notice, having replaced x squared plus y squared with r squared, what we end up with is entirely an equation of cylindrical variables. In other words, this is the cylindrical equation for that same sphere. Not that different from polar. Okay, now this example is a little bit weird for some students. Also, this is an example that illustrates what I think is a nice general point to keep an eye out for, another tool for your toolbox. And I'm going to start off with the general point, looking at this equation here. This is a cylindrical equation. After all, the variables z and r, everything in there is cylindrical variable. And there's another one of these situations where at a casual glance I'm going to get to an immediate, freebie, powerful geometric conclusion. Easy freebie observation. There's no thetas in that equation. Right? Now, let me remind you that last week, I think it was, at some point, not that long ago, we talked about, hey, if you have the equation of a plane, and if it doesn't have any y's in the equation, then that plane, you get a nice geometric conclusion. It's parallel to the y-axis. And, again, that's really nice because it's easy to notice, and you get an interesting and useful geometric punchline, payoff. Same thing here. Because there are no thetas, we get a big payoff. The payoff is this is rotationally symmetric. And the way to realize that is if you think about what do the cross sections look like in different theta slices. Right, various different theta slices that you could take. Each one of these half planes represents a fixed constant value of theta. Okay, well, what happens in this theta slice versus in that theta slice versus in that theta slice? Nothing. Right? Theta doesn't matter. Theta is not even in the equation. That means that all of the cross sections in all of these half planes all look exactly the same. And if all the cross sections, right, in half planes hinged on the z-axis, if all those cross sections look exactly the same, it's rotationally symmetric. So neat observation, something to be on the lookout for. So if I want to understand this, I can pick any value of theta. For whatever reason, I'm just going to take a value of theta like that. I'm going to draw the full. Oh gosh, let me try that again. Draw a full kind of half plane like that, representing that value of theta. What's going on in this half plane? Well, here's there it is. What does this equation look like? Looking at z just as a function of r, in other words, in a zr kind of slice. Z equals a multiple of r is just a line. So our surface, this surface we're trying to understand, is rotationally symmetric around the z-axis, and its cross-section looks like that. And that pretty immediately gives you a cone, like so. Now, one little detail that I deliberately swept under the rug. So I only drew half of a line here. Why did I only draw half of it? Well, because we tend to think of a given single value of theta as only allowing positive values of r. It's just kind of our intuition. We tend to think of, well, if I wanted to go on the other side, I would have picked a different theta. Right? So we tend to sort of think in those terms, but we really don't have to. In fact, this value of theta can be thought of as representing both positive and negative values of r. Certainly z is allowed to be negative, and so really there's nothing wrong with all of these points on this line. So really what you're going to call the theta cross-section is this whole line. So we're not just going to be rotating just that line segment around the z-axis. We're going to be rotating this entire thing, and when you rotate that whole thing around the z-axis, you get the cone here. Let's see if I can. Yeah, something like that. So, the full cone. Okay, how are we doing? Is everybody on board? Okay. One little quick warning. This is just a notational triviality. There is a strong tendency for students who have used geometry and high school algebra, trigonometry, etc., to use r to represent a radius of something, like circle of radius r, or a sphere of radius r, cylinder of radius r, whatever. You can't do that anymore. Tragically, now r is not just a letter of the alphabet to be used for whatever purpose you like. R is now a coordinate, right? And so in the same way that you can't talk about, a circle of radius x, that wouldn't make any sense, right? If you have a circle of radius x, well, wait a minute. No, x is a coordinate. We need x as a variable to describe wherever we might happen to be. You can't use it as a constant also. So likewise, you can't use r as a constant also. So you got to think of something else to call your radii. Now, reasonable choices might be capital R. Perfectly fine, right? Some people like to modify r itself, like r naught. Perfectly fine. You feel free to get creative with it. Some people like to put a tilde over the R. Cool, whatever. Just don't use R itself. Okay. All right. Spherical coordinates. Spherical coordinates are noticeably different from polar coordinates, and yet still spherical coordinates are sometimes referred to as polar coordinates in space. I think this is a really bad idea. Spherical coordinates is importantly different from cylindrical. Cylindrical really is a lot like polar coordinates, but if you're going to say polar coordinates in space, you certainly can't use that term for both spherical and cylindrical. And between the two of them, spherical is the least reasonable choice. So please, definitely do not call this polar coordinates in 3 dimensions. It does not, it's a very confusing and unnatural choice. Okay. All right, so anyway, here we go. What are we going to, what are our coordinates here? Theta is our first coordinate. Good news. It's the exact same theta that y'all recall from cylindrical. Right, it's that angle right there. Think of it as defining a half plane, like so. By the way, I like this phrase here, hinged on the z-axis. You can think of this half plane as kind of like a door, and the hinges that this door is swinging on as theta changes are exactly on the z-axis. So you're going to hear me say this a lot, a half plane hinged on the z-axis. That's what I mean. Okay. All righty. So theta defines our theta half plane. Next, let's talk about phi. This is the lowercase Greek letter phi. Phi represents an angle measured from the positive part of the z-axis into the theta half plane. Importantly, into the theta half plane, not that way, right? This would be for negative values of phi. This here is for positive values of phi. So which direction phi measures depends on what theta you're talking about. Okay. There we go. In fact, I'll go ahead and do this. So, phi is kind of that angle right there. Now, again, awkward. Phi it's a coordinate. Coordinates can be either positive or negative. It's tempting to look at something like this and view it as being as just an angle, something that's intrinsically positive, and again, it's not. Right, now I try to indicate this by drawing a little arrow there indicating the directionality. Directionality kind of subtext is just pretty clear. That means it could go the other way. Subtext pretty clear. That means it could be negative. Like I say, I like to put those little arrows on there. Okay. Either way, these two angles together define a direction. Right, and once you have a direction, why don't I go ahead and do that? Once you have a direction indicated, if you want to represent a point, all you got to do is tell me how far to go in that direction. Now, again, with the how far and the distance and the plus or minus, and again, it doesn't have to be positive, but as a coordinate indicating movement in that direction for positive values, how about that? That tells you, therefore, where your point ends up. And again, negative values a row, just go the other direction. Everybody happy? Okay. All right. A lot of little details there. How are we going to find conversion formulas? I'm going to draw your attention to this triangle. This little triangle right here is critical. It's hard to make sense out of this triangle in this picture because it's inside of a two-dimensional plane, but we're looking at it in a three-dimensional space, and that particular half plane is kind of angled in a weird way, and so things that, like this is a right angle, but it doesn't look like a right angle in the picture. That can be confusing. So just to avoid that issue, I'm going to redraw that triangle. like so. If I can get this to come on, here we go. Yeah. So same triangle, just looking straight on at it instead of looking at it sort of from the side. If you look at and think about the trigonometry of this triangle, everything will just fall into place. So here's the observation I like to make. Let's look at the angle phi. Keep in mind there's phi. So phi is that angle, which means it's also that angle. And phi being that angle, this being a right triangle, we have some easy trig that we can write down. So for example, this side here, which you see from the picture up here, is our r. That's the cylindrical coordinate r. As you see in this picture, that cylindrical coordinate r is easily related by trigonometry to that angle phi. And in particular, it's rho sine phi. Easy trig. And then likewise, the other leg of this triangle being z, I can easily write down, so a little bit more trig, z is rho cosine phi. And I claim this is most of the work, right? Once you realize that this triangle, aka that triangle, gives you easy observations about r and z, everything else falls into place. After all, z is one of our rectangular coordinates, done, right? And r is part of what I already know about x and y. I already know that x is r cosine theta and that y is r sine theta, right? So, like I say, this one picture and this easy trig pretty much immediately gives me my spherical conversion formulas. Now, for your consideration, I've done just a ton of stuff with spherical coordinates in my life. Physics major will do that to you. I never memorized those formulas. I've used them a million times. I've never memorized them. I do not trust myself. I'm quite sure that I would get it backwards at some point. Oh, I would at some point, I'm sure I would accidentally write down rho sine theta cosine phi, right? Or rho cosine theta, or cosine phi cosine theta, and then have z be rho sine phi. I'd get it wrong at some point, and I can't speak for you, but I think you probably will too, right? So my advice on this is make sure you understand this triangle, the easy trig conclusions that you get from this one easy little triangle, and then just always derive these formulas as needed, right? So if you want to remind yourself what this formula is here, right? Well, it's r cosine theta. That you've already memorized, that x is r cosine theta. And then you just have to remind yourself what r is, right? And again, this triangle, easy trig, tells you what r is. I do that in my head every single time I need spherical coordinates for your consideration. Okay. Let's see here. Let me get that. Okay, cool. Okay, another example. Easy relationship to notice between the various variables. This is just kind of a three-dimensional Pythagorean observation, or easy observation about the magnitude of a vector x, y, z, however you want to say it, right? Easy observation to relate those coordinates. And so if you look at this equation, rho equals c, this is going to be an equation of the form x squared plus y squared plus z squared equals c squared, which is a circle. A sphere. Right? They get three-dimensional. So pretty clear how to write the equation of a sphere. Of course, I think this is also pretty geometrically satisfying. After all, rho equals c pretty much tells you distance from the origin is a constant. That screams sphere. Okay, thus the name spherical coordinates. Next example has a bunch of details in it. I am going to leave about half of this example for y'all to look at on your own at your leisure. I'm going to get you started. I'm going to do what I'm going to call the hard half of this question. This little exercise is to point out that there are always 4 ways to write a point in spherical coordinates, just like there's 2 ways to write a point in polar coordinates. Okay, technically there's infinitely many ways because you can always add 2 pi, but aside from this, the freebie of adding 2 pi anytime you want, basically there's 2 ways to do a point in polar coordinate. You can either have theta pointing in exactly the right direction, or you can have theta pointing in exactly the wrong direction, right? And then r just is negative to account for that. Okay, so there's 2 spherical angles and thus 4 sets of spherical coordinates. Okay, for example, let's think about this point right here. There you go. Easy little bit of trig and geometry tells you that that angle is pi over 3 and that angle is pi over 4. Make sure you can do that, of course. But now how do I interpret those as spherical coordinates? Okay, so to get down to business then, one thing I could do, I could interpret this angle as telling me my theta. And I'm going to let y'all think through the rest of the details of how to write the remaining spherical coordinates of the given point using theta equals pi over 3. But let me do the, like I say, the kind of the harder part. Notice that if you add pi to that angle, what that does is that gives you this direction, 4 pi over 3. And I'm going to walk you through now how to think about the rest of the spherical coordinates from the point of view of that value of theta, 4 pi over 3. Okay, so here we go. Don't forget, phi is measured into the theta half plane. Right, so if I'm using theta equals 4 pi over 3, this is where my half plane is. That means that's the positive direction for phi. Okay. But I need to go back this way, so that's clearly going to be just where phi is negative. So with this theta equals 4 pi over 3, my corresponding phi value is going to be negative pi over 4. Is that cool? Something to think about. Okay, and then what is rho? Okay, well between the what I'm looking at, my chosen theta and my chosen phi, I've got that direction. I need to get to that point. The direction is going correctly in the right direction toward that point, so you just pick the positive value of rho, which is 2 square root of 2. All right, what's the other way to do this? Again, the other with 4 pi over 3 as my choice of theta. The other way to get to that point, and this is pretty weird, I will confess, is to realize that if that's the right direction, then that's the wrong direction, and that actually is part of my theta half plane. Let me draw the fuller theta half plane like that. That direction, like, oh, whoopsie. That direction is going to be defined by that angle phi right there. Now, what is that angle? Well, don't forget, this angle here is pi over 4, and between the two of them, red plus green makes a half turn, and so a little subtraction tells you that this angle right here, the green angle, the phi for this workup is 3 pi over 4. Positive 3 pi over 4. Okay, and then last observation with that, defining the direction I'm pointing, right? So for this theta, for this phi, I am pointing that way. This is the exact wrong direction. That means that the corresponding value of rho is negative. Right? Because I have to go, positive would be in this orange direction, and I need to go exactly the opposite of that. So negative value of rho there. Everybody good? Yep.
What's the significance of going like the other way?
What's the what now?
Like, what's the significance of going the other way? Like, why do we?
Yeah, it's just legally allowed, and so it's an option on the table. Now, why would you want to do that? I don't know. Circumstances come up. It's you want to be prepared for any possibility, right? So let's talk about polar coordinates, right? If you think about polar coordinates, why would you want a negative value of r where theta is exactly the wrong direction? We've already seen such an example with this picture, this guy, right? If I want to be able to talk about this equation, r is unavoidably negative sometimes, and so for these values of theta, you find yourself needing to go back the opposite direction. So sometimes it's just imposed on you. Yeah. Okay, good. Okay, so moving along, I think this is a neat observation, that is that the spherical coordinate angles are almost, not quite, but almost exactly longitude and latitude on the surface of the Earth. Well, again, not quite. But if you take your Earth and you put the center at the origin, and if you put the equator in the XY plane, North Pole up on the Z-axis, prime meridian on the in sort of the positive part of the XZ plane. Set it up in the most sort of convenient, natural way. With that setup, notice east longitude is exactly theta. And now, north latitude, not quite such a happy answer. North latitude is measured like that. It's measured upward from the equator. Phi is not. Phi is measured downward from the North Pole. That's a little disappointing, right? But nevertheless, phi and north latitude always add up to pi over 2. And so, again, easy relationship. They're not exactly the same, but easy relationship between north latitude and phi. Okay, and then one last little easy observation. Other than a little bit of lumpiness in the shape of the Earth due to centrifugal force, I don't know if y'all heard this one before, but the Earth is actually a little bit wider at the equator than it is at the poles, to the tune of something like 30 miles. I don't remember the exact number, but it's quite a bit. So ignoring that, pretending like the Earth is a sphere, rho is always just the radius of the Earth, which is, again, basically, plus or minus maybe a percent, pretty much constant. All right, so neat fact. Now, who cares? What is that bias? How does that help me solve problems? Here's a wonderful little calculation allowing us to solve what would otherwise be a very, very hard problem. Now, take a high school geometry, high school analysis approach to this problem. I think you'll find it's intractable, right? But given two locations on the Earth, such as, let's say Durham and, I don't know, what's that, Oslo, something like that, right? How long of a plane flight is that? How far is that along the surface of the Earth? Now notice, of course, you can't just say, the distance between 2 points is a straight line, unless you're going to tunnel, hundreds and hundreds of miles into the magma under the surface of the Earth, which I don't recommend, right? It's not a straight line. You have to go in a curved path. And how would you understand that curve? How would you get what's the foot in the door on that curved path? I mean, you can't view that as part of a triangle, because that's not a triangle. Right? So you can't look at the difference in the longitudes and the difference in the latitudes and play Pythagorean games. It doesn't work. What else you got? It's a hard problem. So very conveniently, the above observation helps us very nicely. If I know the longitude and latitude of these points, which of course is easy from Google Maps, nothing to it, well, then you can immediately write down the spherical coordinates of those points. And once you have these spherical coordinates of these two cities or points or whatever they are, conversion formulas immediately give you the rectangular coordinates of those two cities. Once you know the rectangular coordinates, it's easy to compute the dot product of those two position vectors, right? This position vector and that position vectors. Dot products are super easy to compute in rectangular coordinates. We also know that dot products can be computed as magnitude times magnitude, both of those are the radius of the Earth, times the cosine of the angle, which I'm going to call alpha. So now we've connected a lot of dots here, right? So map coordinates give you spherical coordinates, give you rectangular coordinates, give you the dot product, and since we know the radius, that effectively allows us to solve for this central angle alpha. And once you know alpha, it's all over but the shouting, because after all, that angle and the distance that we're actually interested in are related by an easy old high school geometry formula, like so. So there you go. That's how you compute that distance without any heavy machinery. Everybody happy? Spherical coordinates are the foot in the door that makes that happen, right? Without spherical coordinates, this is much harder. Okay. All righty. Moving along. Last little quick observation about converting equations from, in this case, rectangular to spherical. And again, you can just kind of plug in. You'll see here, for example, I plugged in x is, and then there's our PAT standard formula for converting x into spherical coordinates. So, boom, right? And you could do that with the y and the z and the whole thing and expand and brute force, right, if you want to. But notice, again, it's nice to be on the lookout for convenience, right? I advise always, if there's a convenient trick, take it, right? And the convenient trick here is to notice that x squared plus y squared plus z squared is going to show up, and we already know that's rho squared. So that saves you loads of trouble. And other little details, don't forget that the ones cancel, and boom, 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 and we have that our final result is that this converts to that. Everybody see the process there? Make sure you can check the details, think it through. Right? All right. Okay. Last thing, now this is a really quick observation about standard basis vectors. I believe you already know, you should already know, but just in case, here it is, just to be sure, the rectangular standard basis vectors, otherwise known as standard basis vectors. Sometimes people like to call them IJK, in recognition of the fact that sometimes we have more than 3 variables, which, again, as previously discussed, we definitely do sometimes. I like to call them E1, E2, E3. This is the I think even in mathematical circles, the more typical notation is E1, E2, E3. So anyway, that's standard basis vectors. They play the role that wherever you are in space, these standard basis vectors always point, for example, this one, points in the direction where x is increasing and the other coordinates y and z are constant. Right? So that's one way to think. There's different ways to think about them, of course. But one way to think about them is they point in the direction where one variable is increasing and the other variables are held constant. So you can do that same thing with other coordinate systems. You're going to notice the great big X through all this stuff. You're not responsible for this in terms of it being on the test, but I do want you to know, roughly speaking, what I'm excusing you from, and that is that, again, all the same stuff, same picture in different coordinate systems. For example, if you are at this point right there, actually, why don't I zoom in? There we go. You're at that point right there. You can talk about which direction from this point would have r increasing and theta constant. And that is that direction right there, which we call E sub r. And a little geometry will persuade you there's a pretty handy formula for E sub r. And likewise, E theta, r is instantaneously constant. Et cetera, et cetera. So take a look through all this. I think this is good mathematical weightlifting. This is a good geometric exercise. You'll notice cross products even show up, right? Nice little fact. So good things to think through there. And then don't worry about the details after you've thought it through. And some disappointments. Standard basis vectors and other coordinate systems aren't as useful as rectangular, which, by the way, is why I hardly ever use them. I have no plans to use them in this course. And so that's why you're excused from the details. Okay, so that finishes Chapter 1. We're going to jump into Chapter 2 just a bit. I want to plant some thoughts, and then we'll call it a day in, I think I have 2 minutes there. So there's a bunch of preliminaries to be done here at the start of Chapter 2. It's stuff that has to get said. It's a little dry. Apologies. But it's also foundational, so it's really important to make sure you understand all this. First, I want to clarify what a function is. A lot of people misunderstand and think a function's a formula. That's kind of how they talk about it in single variable calculus and below. Right? But it's important to realize that's not what a function is. A function is a trio of three things altogether. Every one of these is importantly part of what defines a function. So a domain, a target, and a rule of assignment. So the domain is where the inputs into the function come from. You might think of it as the input space. The target is where the outputs from the function go to. You might think of it as the output space. And then the rule of assignment is the what a lot of people think of as the formula. And I just want to point out that, okay, yeah, but it doesn't have to be a formula. Any rule that unambiguously gives you a single output in the target for any given input in the domain is a rule of assignment. It doesn't have to be a formula. So here's a couple of super quick examples, and we'll call it a day. Natural log you're already familiar with. Do notice that the domain for natural log is not all the real numbers, because unless you're doing complex analysis and set up some heavy machinery that we're not ready for in this class, you can't compute or even define the natural log of a negative number. So, positive only. The output's going to be a real number, and of course log is defined in single variable calculus classes. Here's the more interesting example, I think. This function right here. We have a domain, all the students at Duke. We have a target, which is the collection of integers. And the rule of assignment, now I emphasize, not a formula. There's no formula, but the rule is whatever student you give me as the input, I'm going to give you that student's ID number as the output. Perfectly reasonable function, not a formula. Right? And a real quick observation right before we quit, I'll point out that same rule of assignment gives 3 different functions depending on what you consider your domain and your target. So you could consider all possible students. You could define your function as defined on all possible students, or you could say, hey, just the students in this class. That's a different domain, smaller domain. Same rule of assignment. It feels like it's the same function, but it's not, because the domain is part of what a function is. This is therefore a different function and thus a different name. Okay, call it in a day. See y'all later. Have a good one.